Number 1. Unit circle / general Pythagoras. This is the easiest and most commonly used way to prove cos² plus sin² equals 1. Start by imagining a circle of any radius in the xy plane, centered at 0, 0. A general point xy is given by r cos², r sin². This is true for any point that lies on the circle of radius r. This can be seen by dropping a perpendicular from the point to the x-axis. The result is a right-angled triangle, and so by using the ratios of opposite adjacent hypotenuse, SOHCAHTOA and all that, we can show that the x and y coordinates are indeed r cos² and r sin² respectively. R is the radius of the circle, but also the distance of any point from the origin. The square of the distance from the origin is given by x² plus y², which when substituting our general coordinates becomes r² into cos² plus sin²θ. By definition, the distance from any point on the circle to its centre is r, hence d² is equal to r². Dividing both sides by r², yields the desired result that cos² plus sin² equals 1. When dealing with a unit circle, r² is simply 1, so the result comes out quicker. Without the visualization tool of a unit circle, we can still get this result using Pythagoras, simply using the identities of sine and cos in specific contexts of right-angled triangles. Number 2. Matrices. The general rotation 2D matrix for an angle θ counterclockwise about the origin is shown. I won't prove this result for the sake of brevity, but doing so is not that difficult with the aid of a good diagram. The determinant of any 2x2 matrix is very easy, just multiply across the diagonals and subtract. So, working out the determinant of the general rotation matrix, we get cos² minus sin²θ, which just becomes cos² plus sin²θ. 2x2 matrices represent geometric transformations, and the determinant of the 2x2 matrix represents the area scale factor, the factor by which the area of the unit square or any shape in the plane is multiplied by due to a transformation. In a rotation, there is no change of area, thus the determinant must equal 1, leading to the desired result. The same principle applies to a 3x3 matrix. Shown here is a rotation matrix about the z-axis. The determinant of a 3x3 matrix is a little bit more complicated. A general determinant is shown on screen, but you can expand about any row or column. Expanding about the last column is very nice, as there are 2 zeros, so only one 2x2 determinant needs to be computed, which boils down to the same determinant calculation from our 2x2 rotation matrix. This time the determinant represents the volume scale factor, which should still be 1, as rotations will preserve volume. Number 3. Differentiation. Consider a function f of x equals sin² x plus cos² x. If we differentiate it, we get 2 sin x cos x plus minus 2 sin x cos x, as we bring down the power of 2 from both and multiply by the derivative of sin x and cos x, which are cos x and minus sin x respectively. These two terms cancel out, so the derivative of f of x is 0. The derivative of f of x, written as f prime of x, is 0, and that must mean that f of x is a constant. The value of this constant can be found by plugging in any value of x. Since cos and sine are both continuous, plugging in 0 is easiest. F of 0 equals cos² 0 plus sin² 0, which is 1. Method 4. Integration. Doing the opposite of the last one, now let's integrate f of x with respect to x. To do this without using our knowledge that the function is just the constant 1, we need to use our double angle formulae. Cos2x equals 2 cos² x minus 1, so cos² x equals a half cos2x plus 1. Cos2x also equals 1 minus 2 sin² x, so sin² x equals a half 1 minus cos2x. Subbing these into the integral, the cos2x terms cancel out. This leaves half the integral of 2 dx, or just the integral of 1 dx, which is x plus c, where c is an arbitrary constant. The integral of f of x is the same as the integral of 1, thus f of x is 1, leading to the required result. This method isn't very good, as from the integrating step, we could just compare our two expressions for cos2x to get the result, and even then, changing between forms of this identity usually requires knowledge of the identity we are trying to prove. Method 5. The Moivre theorem. The Moivre theorem states that e to the power I theta equals cos² plus I sin²θ. This can be derived easiest through considering Taylor series. The consequences of this is that any complex number, a plus bi, can be expressed in a simple polar or exponential form of re to the I theta, where r is the square root of a² plus b squared, and theta is arctan b over a. R is the modulus of the complex number, how far it is from the origin, and theta is the argument, the angle it makes with the positive x-axis, measured counterclockwise. Consider a complex number where the modulus is 1, r equals cos²θ plus sin²θ, which is 1. This is the same as the first proof pretty much, and shows that re to the I theta describes a circle in the complex plane. Method 6. Hyperbolic/complex definitions of sine and cos. The hyperbolic functions cos and sine are defined by adding and subtracting exponentials respectively. As can be shown from the Moivres, sine and cos can be expressed in similar form to hyperbolic functions as shown. Squaring and adding turns the half into a quarter, so 4 on the denominator. When squaring our complex expression of sine, the 2i in the denominator becomes minus 4, as I squared is minus 1. This negative can be moved into the numerator by multiplying top and bottom by minus 1, hence the subtraction shown. Expanding the brackets we get this, and all the squared terms cancel, leaving just the cross terms. When multiplying exponents of the same base, we add the powers. So we can take out the factor 4 to get 4 times e to the 0 divided by 4. The 4's cancel out, and anything to the power 0 is 1, so this simplifies down to 1, thus proving the trig identity. Method 7. T-formulae. The t-formulae are based on a very simple substitution that can make difficult integrals and trigonometric equations easier to solve. It is simply t equals tan theta over 2. This can be seen from the following triangle. Using the double angle formulae, we can derive the formula for sine theta and cos theta in terms of t. Squaring and adding these expressions gives us 1 minus 2t squared plus t to the 4 plus 4t squared over t plus 1 all squared. Adding in the numerator gives us t to the 4 plus 2t squared plus 1, which is the same as t plus 1 all squared. Thus the fraction is simply 1, proving the trig identity. Method 8. Using the compound angle formulae. This one is probably my favourite, as it's just so slick and so simple. Anyway, cos A plus B equals cos A cos B minus sin A sin B. If we let A equals minus B, cos minus B plus B equals cos minus B cos B minus sin B sin B. Since cos is symmetric about the y-axis, it's an even function, cos minus B equals cos B. Since sine is an odd function, sin minus B equals minus sin B. Minus B plus B is obviously 0, so now we have cos 0 is equal to cos squared B plus sin squared B. Cos 0 is just 1, so we get our desired result. Method 9. Complex factoring. The difference of two squares is a useful algebraic trick in simplifying expressions. A squared minus b squared is the same as a plus b multiplied by a minus b. In the realm of real numbers, there is no such neat factorization of a squared plus b squared. However, allowing for complex numbers, we can express this too as a difference of two squares, a plus bi multiplied by a minus bi. Letting a equals cos x and b equals sin x, we get that cos squared x plus sin squared x is equal to cos x plus I sin x multiplied by cos x minus I sin x. From the Moivres, we know that the original expression is e to the I theta, and the second bracket becomes e to the minus I theta. Once again, multiplying exponents of the same base means adding the powers, which leads to e to the 0, which is 1. There are likely more ways to prove this trig identity, the primary way not being mentioned through the use of Taylor series. However, I'll leave that one for you to discover. That's my admission that I'm not smart enough to do it. Thanks for watching. Please subscribe for more random videos on science, maths, or really anything else I feel like.